Our topic for today is random variables, which are variables that take on a random value. Random variables are fundamental to all of statistics, where they are used to model all sorts of probabilistic occurrences, but they have a somewhat counterintuitive definition. Intuitively, a random variable is a variable that can take on various values, and which value it takes on is random. But our definition is that a random variable is a function. The reason we define it this way is because the random variable is built on some underlying sample space, and the sample space gives us the randomness. And then we can define a function that maps the outcomes in the sample space, which occur randomly according to our probability function, into the values that the variable can take on. So the possible values of the random variable are the image of the function, and the domain of the function is the set S from our sample space. To make sense of this definition, let's look at some examples. And for all of our examples today, we'll use this as our sample space. So this sample space is similar to our 2 dice example from last time, but now one of the dice is weighted such that it has equal probability of landing on 1, 2, or 3, but higher probability of landing on 4 or 5, and the highest probability of landing on 6. So when we roll the pair of dice, where one is fair and the other is weighted, we have a 1/60th chance of landing on any of the outcomes on the left-hand side. We have a 2/60th chance of landing in any of the outcomes in these 2 columns, and for each of the outcomes in the rightmost column, we have a 3/60th chance. So using this sample space, where the outcomes are pairs of the value on the first die and the value on the second die, let's define some random variables on this sample space. If our sample space is these pairs of die rolls, then each outcome, S, consists of S1, which is the roll of the first die, and S2, which is the roll of the second die. And so a very natural random variable when rolling 2 dice is the sum of the values on the 2 dice. So here, the random variable can take on values from 2 through 12. So this random variable maps an outcome which lives in the sample space to a total that lives in the set 2 through 12. And so the values that this random variable can take on are 2, 3, 4, up to 12. And so when the outcome in the sample space is 3, 5, the value of this random variable would be 8. Another random variable we could define would be to take for any pair that is one of the outcomes, just the first element of that pair, namely the value on the first die. So this random variable maps our outcomes to integers between 1 and 6. We could similarly define a random variable that extracts the roll of the second die, which would have the same set of possible values as the first die, though those values happen with different probabilities. But we could also define lots of other random variables on this sample space, and they could be arbitrarily complicated. But an example that might make sense in terms of rolling dice would be to take the high roll among the two. So this random variable would take on the value of the larger of S1 and S2, but this means that the possible values it could take on are still the numbers 1 through 6. So far, all of our random variables have had numbers for the values they could take on, but just like we can have variables stand for other objects besides numbers, we could have random variables that map our sample space to non-numerical values. And one thing we might be interested in with two dice would be the ordered pair with the higher of the two rolls and then the lower of the two rolls. And if we think about the set of things that can be produced as the values of this random variable, it's all pairs of two integers between 1 and 6, where the larger of the two integers comes first. So it's often useful to distinguish the random variables that produce numbers from those that produce other sorts of objects. And so we define a random variable to be real valued if the values that it can take on are real numbers. So if the set of values that the variable can take on, that is the set of outputs of the function, is a subset of the real numbers, then we call the random variable real valued. And so among our examples, x, y, z, and w are real valued random variables, but t is not real valued. Because we've defined our random variables in terms of a sample space, we can use the language we've already developed for talking about random outcomes and events in the sample space to think about the randomness of our random variable. Specifically, we can think about what values the random variable takes on with what probabilities by thinking about events in the sample space. Because we defined our random variables as functions that map outcomes in the sample space to values that the random variable takes on, we can think about the event in the sample space where the random variable takes on a particular value. So for example, our random variable y, where the value of the random variable corresponds to the roll of the first die, can take on the values 1 through 6, and so each of those values of the random variable having value 1 or having value 2 and so on, corresponds to an event in the sample space, and those events are non-overlapping and cover the entire sample space. For the variable y, the event that it has the value 1 corresponds to the first row of our table representing the sample space. For z, where the value of the random variable is the roll of the second die, the different values that the variable can take on correspond to the columns in our chart. For x, if we think about the event that x takes on the value 2, the subset of s corresponding to x having value 2 is all of the outcomes where the total roll is 2, and so that is just this top left outcome. X equals 3 is the subset of the sample space containing these two outcomes. And if we think about the event for x equals 5, that consists of all of the outcomes in the sample space where the total roll is 5, and so that will be these 4 events. But again, when we divide the sample space up into the events for each of the possible values the random variable takes on, we will have partitioned the set S into subsets that are non-overlapping and cover the entire space. For W, our high roll random variable, where the value of the random variable is the larger of the two dice rolls, if we think about the event W equals 3, that is the subset of our sample space where the larger of the two dice rolls was 3. So that event consists of the outcomes where 3 is the larger of the two rolls. Similarly, the event W equals 6 would be all of the outcomes in this subset of S, which again forms a backwards L. And for T, we have many more events, one corresponding to each of the possible pairs that could be the value of our random variable. And so if we think about which other outcomes are in the same event as 5, 4, well, that's the other die rolls that have a 5 as their larger roll and a 4 as their smaller, and so that would just be this other outcome. And for any given outcome, the one that is symmetrically opposite it in our diagram is the only other outcome that's in the same event. So now that we have a sense of what some of the events for the random variables taking on different values look like in our chart, let's think about the probability of some of those events occurring. For our random variable x, we can ask what is the probability that it takes on the value 4, and we denote that by extending our notation for probability to random variable equals some possible value. And so when we talk about x equals 4, we are talking about the event that the random variable takes on this value, which, as we said before, corresponds to this 3-outcome subset of our sample space. But since we're thinking of x equals 4 as an event, we already know how to calculate the probability of an event. We just add up the probability of each of the outcomes in that event. And so when we add up the probability of these 3 outcomes, we get a 20th. If instead we calculate the probability that the random variable W takes on the value 4, now we're calculating the probability of the backwards L-shaped event that included all of the outcomes where the larger of the two rolls was 4. And so if we add up the probability of all of the outcomes in this event, we get 1/60th plus 1/60th plus 1/60th plus 4 times 2/60ths. So we get 11/60. So now that we know how to calculate the probability of a random variable taking on different values, we can think about the relationship between different random variables. And specifically, we can think about when two random variables are independent. So we say that two random variables are independent if, for every pair of values they could take on, the probability of the joint event that x takes on the first value and y takes on the second, those events are independent. So this expression corresponds exactly to the one from our definition of independent events. And, as we said before, x taking on a particular value is an event, and y taking on a particular value is an event. And so we are saying here that the events x takes on value A and y takes on value B are independent events. And so we call the random variables independent if, for all pairs of events, for x taking on one of its values and y taking on one of its values, those events are independent. And just like we had several equivalent definitions for independent events, we could have instead defined independence of random variables in terms of conditional probabilities not changing no matter which value of the other variable you condition on. So using this definition, let's think about whether any of our random variables are independent. If we're considering whether x and w are independent, then we need to think about all pairs of values that x and w could take on. There are 11 different events of x taking on one of its possible values and 6 different events for w. And so all 66 pairs of events must be independent for the two random variables to be independent. So we should be able to either prove that all of those pairs of events are independent, or show a counterexample of some event for x taking on a value and some event for w taking on a value where those two events are not independent. And so let's think about these events that we have already considered, x taking on the value 4 and w taking on the value 4. And here I will use the equivalent definition of independence of events in terms of conditional probabilities. So for these two events to be independent, it must be the case that the conditional probability is the same as the probability that x was 4 unconditionally. If we're conditioning on w having the value 4, then we know that we are in this subset of our sample space, but x takes on the value 4 in only these 3 outcomes, and so the probability of x being 4 given that w is 4 is 0. And the unconditional probability of x being 4 was a 20th, and so because the probability changed when we conditioned on this event, that means that the events x equals 4 and w equals 4 are not independent, and that in turn means that the random variables x and w are not independent. So then, is there any pair of random variables among those we have defined that are independent? Well, We had last time an example of independent events where one event depended on the first die and the other event depended on the second die. And here we have two random variables where the events for y all depend only on the first die, and the events for z all depend only on the second die. And so in fact, all pairs of an event for y and an event for z are independent, and so y and z are independent random variables. To prove that y and z are independent, we would need to show that for all 36 possible values that y and z could jointly take on, conditioning on the value of z doesn't change the probability of y taking on the value I. At the beginning, I motivated random variables as foundational to statistics, and so we'd like to think about statistics that we can define in terms of random variables. Most of the basic statistics one would want to define make sense when random variables have numerical values, that is, real-valued random variables, and for such variables we can think about, for example, the average value of the random variable. But because the values that occur are random, it makes sense to incorporate that randomness into the average and compute a probability-weighted average. So the basic definition of the expectation of a random variable is the sum over all of the outcomes of the probability of the outcome times the value for the outcome. And this is like an average value in that we are adding up all of the values, but rather than dividing by the number of values, we are reweighting by multiplying each value by the probability of the outcome that gives us that value. But this sum over all of the outcomes is often tedious to compute, and it's often easier to group together all of the outcomes that have the same value. And if we do that, then we can rewrite this as a sum over the different values that the random variable can take on. If we gather together in this sum all of the outcomes that have the particular value little v, then when we add those up, we will have a little v as the variable's value for all of them, multiplied by the sum of the probability for all of those outcomes, which is the probability of the event that x takes on this value. And so gathering up all of the terms with the same function output here gives us one term of this sum, and in all of our examples here there are far fewer terms in this sum, so it's often easier to compute. If we want to compute the expectation of our random variable x, then by the first definition, we would have this sum over all of the outcomes in our sample space, which has 36 terms. Or by the second definition, we have this sum with 11 terms. So I'd rather do this one. In this sum, our first term is when x takes on the value 2. So we'll have 2 times the probability that x is 2. And the probability that x is 2 is 1/60th. The next term is when x takes on the value 3. And so we'll have 3 times the probability that x is 3. And that probability is 2/60ths. For value 4, we have 3 of the 1/60th boxes. For value 5, we are talking about the probability of this event, which is 1 plus 1 plus 1 plus 2 over 60. So when we expand out our sum and figure out the probability of each of these events, we have 11 terms. So let's multiply out all of those terms and combine them. So when we add all these up, we get a probability weighted average of 7.7 for the expectation of our total roll on these 2 dice. That makes sense if you're familiar with normally rolling 2 dice, where the average value is 7. Since we've weighted one of the dice towards higher values, our expectation, the average roll, should be slightly higher than 7. But could we have calculated this expectation in an easier way? Well, yes, we could have by taking advantage of linearity of expectation. Linearity of expectation allows us to break expected value calculations down if our random variable is the sum of other random variables. And in this case, our random variable x is the sum of y and z. And so once we know how to combine the expected values of y and z to get the expected value of x, we have another way of computing this expectation. Linearity of expectation is about performing linear operations on our random variables. A linear function comes from multiplying a variable by a constant or adding 2 variables. And so if we multiply a random variable by a constant, then we multiply the expectation by a constant. And if we add 2 random variables, then we can add their expectations. The proof of part 1 just relies on factoring a constant out of the sum from the definition of expectation. But for part 2, it's worth going through the proof. For part 2, we start by defining a random variable that is the sum of 2 other random variables. And so we're thinking about the expectation of our random variable z. By our definition of expectation, the expectation of z is this probability weighted sum over all of the outcomes. And because in our hypothesis we defined z to be x plus y, we can substitute for z. we can distribute multiplication over addition. We can split up the sum by collecting all of the x terms and all of the y terms into separate sums. But this is the definition of the expectation for x, and this is the definition of the expectation for y, and so we've shown that the expectation of our variable, which was x plus y, is equal to the sum of the expectations. Of note, I did not anywhere in this proof rely on x and y being dependent or independent random variables. Linearity of expectation holds for any two random variables. So returning to our example random variables, x is the sum of random variables y and z, and so we should be able to use the linearity of expectation to compute the expected value of x as the sum of the expectations for y and z. The expectation of y is the sum over all of the different values y could take on, which correspond to the rows of the value times the probability. But y, being the fair die, lands on each row with probability 1/6. So this sum is just 1/6 plus 2/6 plus 3/6, and so on. And when we compute that value, we get an expectation of 3.5, which should make sense because we have possible values 1 through 6, all of which have equal probability. And so when we average the values 1 through 6, where they all have the same weight, we should get the average of the numbers 1 through 6, which is 3.5. By linearity of expectation, this also gives us the result that the average value of 2 dice, if those dice are both fair, should be 7. For z, the events that we are summing over correspond to the columns, which have probabilities of 1/10, 1/10, 1/10, 2/10, 2/10, 3/10. And so value 1 happens with probability 1/10, value 2 happens with probability 1/10, value 3 has probability 1/10, but the value 4 has probability 2/10, so we have 2/10 times 4 in our sum. We also have 2 times 5, and the value 6 happens with probability 3/10, and so we have a 3/10 times 6 in our sum. And if we carry out all of this arithmetic, we get an expectation of 4.2, and so then the expectation of x is the sum of these two expectations, or 7.7, which gives us the same result we computed before. Apart from averages, probably the most commonly computed statistic is variance. Variance is defined as the expectation of the squared difference between a variable and its expectation. So let's break that down. The expectation of variable x is the probability weighted average value for that random variable. And so we can think of that average as the center of the range of values that x can take on. Then we are taking the expectation of a new random variable that we have defined as the squared difference between x and its expectation. And so if the expectation gives us the center of how x's values are spread, then we are taking the squared difference between values of x and the center of the distribution. And so the variance is the average squared difference from the center, where we are averaging over all of the different values that the variable can take on, the difference between that value and the central value squared. So why is this useful? Well, it gives us a measure of how spread out the variable is. If most of the values that the variable can take on, or most of the ones that it takes on with high probability, are close to the center, then most of the time this difference will be small. And so when we take the average of the squared differences, we will get a small variance. But if some of the values are really spread out, then for those values, we will get a large difference from the center. And if those spread out values have high probability, then when we compute the average squared distance from the center, we will get a large variance. So if the values that the variable takes on are close to the center with high probability, then we'll have a small variance. And if they're spread far from the center with high probability, then we'll get a large variance. As an example, let's compute the variance of our random variables y and z, and take a moment now to think about which you think is more spread out. Y, where we have the values 1 through 6 with equal probability, or z, where the higher values have greater probability. We calculated the expectation of y as 3.5, so we're going to be adding up squared differences from 3.5. So we have a 1/6 probability of the value 1, a 1/6 probability of the value 2, and so on, where for each value we are taking the difference between that value and the expectation, squaring it, and multiplying by the probability of that value. And if we do all this arithmetic, we get a value of approximately 2.92. This value doesn't mean very much unless we have something to compare it to. So let's also calculate the variance of z and see which has the larger variance, so we'll know which is more spread out. For z, we are again computing squared differences from the expectation. We calculated that the expectation of z was 4.2, so we'll take 1 minus 4.2 squared, 2 minus 4.2 squared, and so on, and multiply each of those by the probability that the value occurs, where those probabilities are 1/10 or 2/10 or 3/10. And when we do the arithmetic here, we get a variance of 2.76, which means that z is less spread out than y. So how does this make sense? Well, for y, we have values that are equally likely to be spread far from the expectation in both directions, whereas for z, we have more probability on the larger values, and we also have a larger expected value. And so with an expectation of 4.2 and more of the probability on the values that are closer to 4.2, we have more of the probability clustered close to the expectation, and so in our probability weighted average, Z is less spread out than Y. There's far more that we could do with probability and statistics, but unfortunately, that's all we have time for this semester.